Hello once again. This time around we're going to take a look at inverse sine, inverse cosine, and inverse tangent. So three more elementary functions. So we've already taken a close look at the sine function, the cosine function, and the tangent function, which, as we know, they take inputs that are real numbers, can be thought of as angles, and they output ratios. They're basically the names of ratios that we find off the unit circle. And then depending on the which function we're talking about, the outputs sometimes are all real numbers, the outputs sometimes are not. So in the case of sine and cosine, the outputs are always a number between -1 and 1, including -1 and 1. Whereas in the case of the tangent function, it can actually output any real number. So now we're going to take our knowledge of inverse functions and apply it to sine, cosine, and tangent. So as we discussed earlier, every collection of ordered pairs, which we call a relation in mathematics, every collection of ordered pairs has an inverse. They all have inverses. You can take any collection of ordered pairs, and if you just simply swap the positions of each pair, so you take the abscissa and the ordinate that are paired together and change their places, you get a coordinate, an ordered pair that's on the inverse. But as we also mentioned, when you do that, the result is not always a function of x. So that's going to come into play here. So let's start with the sine. We're going to spend the most time on the sine function and try to get a feel for what's going on with it. And then cosine and tangent will speed up a little bit and not go into as much detail since it'll be very similar to what's going on with the sine function. All right, so let's quickly revisit some of our inverse function information. Okay, so for a typical sine function, you know, if you've got f of theta is equal to sine theta, that's just a typical sine function. You normally would input a real number. It can be thought of as an angle. So for example, you could input pi over 6. You could input 30 degrees or pi over 6 radians. And then you want the sine ratio for pi over 6 radians. So you draw a unit circle, you get your coordinate on the circle, and you find the sine ratio, which is y over r, which is 1/2 off the unit circle. So your input is pi over 6, and your output is a ratio. So what's important here is that the input we thought of as an angle, and the output was a ratio. Well, now we want to investigate what would happen if we changed places for the input and output. That's what an inverse is, right? The input becomes, we change it. So if it's theta as the input, that'll now become the output. We're going to change positions. So if we use x and y notation, the input would be x, the output would be y. But we want to think about what if we change those positions? What if the domain became the range and the range became the domain? So that's what we're going to investigate. But before we get too far ahead of ourselves, let's remind ourselves some of the just kind of generic inverse function information that we're going to need. For example, let's revisit this idea of being 1-to-1. So a 1-to-1 function is a function, that's why it's in the name, right? It's called a 1-to-1 function, is a function where every, that's terrible handwriting, where every output is paired with exactly one input. Now keep in mind though, it's a function, so that means every input is paired with exactly one output. Now we're saying along with that, every output is paired with exactly one input. So another way to think of this is the marriage of x, oops, I need of twice too either, of x to y is monogamous. Did I spell that right? So every x is married to one y, and that y is married to just that one x. They're just seeing each other, and that's it. Now, the reason we cared whether something was 1-to-1, so this is important, the inverse of a 1-to-1 function is also a function of x. So if you start out with a function of x, and that's a 1-to-1 function, its inverse will also be a function of x. So the inverse of a 1-to-1 function is also a function of x. That's why we cared. If we knew a function was 1-to-1, we knew its inverse would also be a function of x. It would pass the vertical line test. But here's the thing, right off the bat, our sine function is not 1-to-1. It's not a monogamous relationship between x and y. So to convince yourself, I'm going to do a few things here to try to convince you that it's not 1-to-1. The first thing is, let's just do some numerical analysis. If I do sine of pi over 6, the output is a half, right? We saw that earlier up here. But if I do sine of 5 pi over 6, it's also a half. I just found two inputs that are paired with the output of 1/2. So as a coordinate, this would be pi over 6 1/2, and then this one as a coordinate would be 5 pi over 6 1/2. So this y value of 1/2, it's dating two different x values. It's dating pi over 6 and it's dating 5 pi over 6. So it's not a monogamous relationship. So the sine function is not 1-to-1. Therefore, its inverse will not be a function. You know, you might be thinking, who cares? Well, if we have a function, if we have a relation and it's a function, that means every time we plug in an input, we get exactly one output out. And that's convenient. It's very convenient. So there's nothing wrong with having a relation where you give it an input and you get an output. Sometimes you get more than one output, or your outputs are married with more than one input. I mean, there's nothing inherently wrong with that. However, it's very convenient that when you give it an input, you know you're going to get one and only one output back out. So inverse sine is not going to be a function of x. At the end of the day, it's not a huge deal. However, it would be very convenient if it was. So we're going to spend a little bit of time talking about how, even though inverse sine is not a function of x or theta or whatever variables you want to use for your inputs and outputs, we actually are going to make it be a function of x. So let's look at a graph of sine real quick. We're just going to do a quick sketch of sine, nothing too fancy. So we know that at pi over 2, we get up to 1. These are not scaled the same. Obviously, pi over 2 is actually a little bit bigger than 1, but I've got this being, I guess I could try to do the scale a little bit better. So let's say that's pi over 2, which is 3.14-ish divided by 2, so that's a little bit bigger than 1. And let's have 1 be here. So at pi over 2, you're at 1. And then at pi, you're at 0 for sine. And then at 3 pi over 2, you're at -1. Sine of 0 is 0, and then going in the other direction, you're at -1, 0, and you're back up at 1, right? The sine function looks like this. So I missed my dot down there, so I'm going to fudge it a little, but just make the dot bigger. So our sine function looks like this. Now, it's not 1-to-1. We already showed that numerically up there, but now we can see graphically why it's not 1-to-1. It fails the horizontal line test. So it hits this curve an infinite number of times. If I draw any horizontal line between -1 and 1, it's going to hit this curve an infinite number of times. So it hits it more than once, therefore it fails the vertical line test. So y equals sine of x fails the horizontal line test. All right, so its inverse is not going to be a function, but we would like it to be a function. We would like it to be a function. So here's what we do. We say, okay, I failed the horizontal line test because this graph goes on and forever. Its domain's all real numbers, so it just keeps oscillating back and forth between -1 and 1. So what we want to do is we want to restrict the domain. The domain's causing a problem here. The domain, being all real numbers, allows for horizontal lines to hit this graph more than once. So here's our goal. Our goal is to restrict the domain while maintaining the range. I want the range to be kept the same. So I want my graph to go from -1 all the way up to 1. I want all those y values kept. I don't want to lose them. So I want to keep the range, but I want to restrict the domain. Now, it turns out there's lots of ways to do this. So for example, one way to do this is I could just simply use -3 pi over 2 all the way over to -pi over 2. If I just use this piece of sine, this chunk right here that's orange, if I only use that orange piece, I keep my entire range, but it will now pass the horizontal line test. I will hit that once and only once when I draw horizontal lines. So its inverse will be a function. I could do that. And there might be a reason to do that depending on what you're doing with your sine function and your inverse of it. Another option is I could do -pi over 2 up to pi over 2. Now the benefit there is it allows for some negative numbers, it allows for some positive numbers, and it allows for 0. So there's a variety of x values still left in that domain, whereas the first one I showed you would only use negative numbers as its domain. Okay. This one lets me use some negatives, some positives, and zeros. Another option would be I could do from pi over 2 down to 3 pi over 2, but again, the downside to it doesn't allow zeros not in the domain, and zeros are pretty common numbers. Zeros are a pretty important number. It also doesn't allow for negative numbers in the domain. So again, just kind of, what's our goal here? What are we trying to do? What's the most versatile way to do this? And there's an infinite number of ways I can do this, right? I can, as long as I pick any top of the hill, any relative max down to any relative min on the graph, it's going to get the job done. It's going to keep the range, restrict the domain, allow me to be a one-to-one function. And it turns out the kind of common agreed upon restriction is this one here, where we go from -pi over 2 up to +pi over 2. So we're going to restrict the domain of the sine function to -pi over 2 to pi over 2. So to create a one-to-one function for y equals sine of x, we restrict its domain again, terrible handwriting. We restrict its domain to be all x that go from negative, man, I need double negative there, to go from -pi over 2 up to pi over 2 instead of all real numbers. Okay, and that's what I've got. That's what I've got in orange in my graph. So if I do that, look what happens. The moment I don't allow for any of these x values, none of them, all of them are gone. The rest are just gone. The moment I do that, I now have what's left. It is a function. It passes the vertical line test, but it's now one-to-one because it passes the horizontal line test also. So when I go to do its inverse will be a function of x. So we basically take the sine function, which its inverse was not gonna be a function of x. We restrict the domain to -pi over 2 to pi over 2, and what we're left with is a one-to-one function, therefore its inverse will be a function of x. So we've accomplished our goal. Now again, there's nothing wrong with the inverse of sine not being a function. And there might be a time when you're working with data where you actually don't want it to be a function. You want all the possibilities that come with inverse sine. That might be a thing that you want at some point. However, our goal here is if we want to take the sine function and make it 1-to-1 so that its inverse will be a function, this is how we would do so. And by the way, this is how this restriction is what every calculator I've ever used uses. Every math software that has the inverse sine function in it, this is the restriction any of them that I've ever used uses. So this is a pretty common restriction. So we shouldn't run into any problems with any technology we then use. All right, so let's look at this a little bit more closely, a little bit more precisely, rather than me sketching these things. So let's quickly go back through what just happened here. So here is the sine function. Here's our sine function. It's graphed way more accurately than I ever could. So here's pi over 2, 1. There's pi 0, 3 pi over 2, negative 1, 0, 0, so on and so forth. As you can see, it passes the, it passes the vertical line test, no problem, because it's a function. It's a function of x, if x is your input. So no issues here, it's a function. However, when you go to do its inverse, so if I take every single one of these coordinates that you see plotted in blue, and yes, that's a lot of coordinates all connected together to make the curve, let's not forget that, and I flip them, I flip each pair, so the input becomes the output becomes the input, and I graph it, I end up with this. And as you can see, this is its inverse, and it fails the vertical line test miserably. The inverse is not a function. It is not a function. You might be thinking, wait a minute, why does the graph look like that? Let's not forget how inverses work. You pick any coordinate, so say you pick pi over 2, 1. You just flip them, and that's a coordinate on the inverse. So pi over 2, 1, pi over 2 is a little bit bigger than 1. Pi divided by 2, 3.14159, divided by 2 is a little bit bigger than 1, comma 1. So then you would go right 1, up, something a little bit bigger than 1, pi over 2, and you get this coordinate. So this coordinate right here becomes this coordinate right here when you reverse them. And 0, 0, when you flip 0, 0, you get 0, 0. So it passes through the origin also. And then remember, the domain becomes the range, and the range becomes the domain. So for regular sine, its range was negative 1 to 1. And when you look at inverse sine here, its domain is negative 1 to 1, right? Here, negative 1 would be right about here, because this is a little bit smaller than negative 1. It's a little bit further away from 0. This is positive 1 right here, because this is a little bit bigger than positive 1. So now its domain is negative 1 to 1, and its range is all real numbers. Now, domain and range, it's not a function of x, but you get the idea. The outputs could be any real number here. But it's not a function of x. It is not a function of x. It fails the vertical line test miserably. So we're trying to avoid that. This thing is a function of x. We like that. So what we do is we restrict its domain to negative pi over 2 to pi over 2. And then we only use that part. So here's the entire inverse for sine, not a function of x. Here's what we get if we only use the part that we had here, right? Here's my orange part, there it is. And if I flip that, here it is, right here. Let me get rid of the whole thing. There it is in all its glory. And now it passes the vertical line test. So it's a function. So when I use this version, we'll talk about this notation in just a sec, but when I use this version of the inverse, not this version, this one's not a function of x. This version is, though. So this is the version you get when you take sine and only use negative pi over 2 as its, or up to pi over 2 as its domain. Okay, so this is going to be our new elementary function is inverse sine, the inverse sine function, the inverse sine function. And we're also going to do inverse cosine and inverse tangent as functions. So we're going to do something very similar for 2 more of our trig functions. Okay, let's go back to this. All right. And then again, it's important we understand other restricted domains were possible. Now, so why do we choose this one? Again, I mean, I guess the most practical reason is this is the restriction that technology uses, so calculators and mathematical software. But, I mean, again, there's something to be said about the fact that the restricted domain allows for some negatives, some positives, and zero, so a variety of inputs. Okay, so going in the Wayback Machine, recall that any coordinate, any ordered pair, any abscissa and ordinate on the graph of a particular function, if you just reverse those positions, so B is now the abscissa and A is now the ordinate, then you get that is going to be an ordered pair on the graph of its inverse. So if we apply that to our sine function, so here's our sine function. This is the traditional sine function right here that we've been studying for a while now. We restricted its domain to be negative pi over 2 to pi over 2. Well, now we're going to flip x and y. So this domain is now going to become the range for its inverse. So it's going to be all y's such that y is negative pi over 2 to pi over 2. So that's important. The inverse of sine outputs numbers that can be thought of as angles. The inverse of sine, like I can't say that enough, the inverse of sine outputs what can be thought of as angles. So if we apply this to the range, the outputs of the traditional sine function are now the inputs of its inverse. So it's all x such that x is between -1 and 1. So over here, if you take y equals sine of x to create the inverse, you get x equals sine of y. That's the inverse. So this is the inverse of y equals sine of x. All right, but we've been here before. When we did exponential functions, right, we did y equals a to the x, and then we swapped x and y. That was the inverse. The problem was we wanted to solve for y, and we couldn't. So we solved for y by inventing new notation. We said that y is log base a of x, simply because we wanted y by itself. We like all our functions of x to be y equals some explicit expression using only x's. And you couldn't do that with the inverse of an exponential function. You had y equals a to the x, and then you inverse that bad boy, and you get x equals a to the y, and you can't solve for y. There are no rules in the real number system that allow you to solve that for y. So instead, we invented some notation, the log notation, to allow us to do that, that y would equal log base a of x. So now we have to do the same thing. So this is the second time now that you've seen this in your study of the real number system. We've got x equals sine of y. That's the inverse. However, we want to solve it for y. We want y to be by itself. So we're going to invent some notation, arcsine. So A-R-C-S-I-N, arcsine. So right here, these are equivalent. These right here are equivalent. That's important. These are equivalent. So y equals arcsine of x is the inverse of sine. Now, arcsine is the notation I prefer to use. However, in the last so many decades, another notation has come into popularity, and that's using the little -1 in the superscript position on the third letter of the name of the ratio. So y equals sine with a little -1 in the superscript position of x. That's also, and this is also equivalent. These are all equivalent to each other. So you'll see this one too. And we have to use both because both are now actually pretty prevalent. You'll see both. You'll see the new one on calculators a lot because it saves space. You'll see some of the older teachers and professors and textbooks use arcsine because that's what we've been using for years. It's easier to type. So I prefer to type it that way. So we kind of have to know both. It's a weird thing. We typically don't have competing notation in a lot of what we study. but this is one of those times where we do. So just keep that in mind. Arc sine and sine with a little -1, those both mean inverse sine. But super important to understand that inverse trig functions, so we've only looked at sine so far, but we're going to do all 6 of them eventually. So inverse trig functions output angles. Inverse trig functions output angles. So what their main use is when you have a situation and you've got some measurements, but you don't know the angle that resulted in those measurements. All right, so you don't know the angle. So you need something that can give you the angle. You need something that can, the input are the measurements you have, the linear measurements that you have, and you need the output to be the angle that resulted in those. Well, in steps and inverse trig function, that's what they're good for. And you're going to see that because we do lots of applications. All right, so here we go. We're ready to formally define the inverse sine function. If y equals sine of x, then x equals sine of y, or y equals arc sine. That's a C again, my handwriting. Getting a little sloppy. Is the inverse. Here, since we typically always use the restricted domain, and we always want the inverse to be a function of x, let's go ahead and actually, I guess I did word it that way. I did say inverse sine function. So let's be careful to make sure that what we're writing, we're definitely talking about the inverse that is definitely a function itself. So let's start that. Let's try that again. So if y equals sine of x, where x is between -pi/2 to pi/2, then x equals sine of y, or y equals arc sine of x is the inverse. Where x is between -1 and 1, and y is between -pi/2 and pi/2. So if you start with the traditional sine function, the parent function, and you restrict the domain to -pi/2 to pi/2, then x equals sine of y, or the preferred way to write it, y equals arc sine of x, is the inverse, where x is between -1 and 1 inclusive, and y is between -pi/2 to pi/2 inclusive. And again, note y equals sine with the little -1 as the superscript on in. Is another way to denote we are going to use both ways to write that. Okay. I said this earlier, but I've got it in here again because it's so important. When evaluating an inverse trigonometric function, the angle is being sought after. So you're plugging in a ratio and you're getting back an angle. That's important. It's backwards, hence inverse, than traditional trig functions. So let's give this a try. So let's say I want to know what arc sine of -1/2 is, right? So we've got our function, y equals arc sine of x, and now I want to plug in -1/2. So now I want to evaluate it. I want to plug in -1/2. What's important is that this is the ratio from our circle. That's backwards. Normally, you don't know the ratio. Normally, you know the angle to draw on the circle, and you draw the angle to get the ratio. We're doing it backwards now. We're saying, hey, what angle do I have to draw to get that ratio for sine? So let's see here. We should probably write that for this first one. This is asking us to find an angle y such that it's got to be between -π/2 and π/2, whose sine ratio is 1/2. I mean, that's in words, that's what we're being asked to do here. Oh, -1/2, sorry, it was -1/2, wasn't it? So I have to go looking for an angle from -π/2 to π/2 whose sine ratio is -1/2. So we're going to draw a picture. I mean, why wouldn't we? We've been drawing a picture for all the other trig stuff. So here we go. Here's our unit circle. I've only drawn half of it because I'm only looking for angles from -π/2 to π/2. So I'm only looking for angles that go down to here or angles that go up to here. That's all. That's it. It's the only angles I'm considering. And I want sine to be -1/2. Well, sine is negative in quadrant 4. Right, sine's negative in quadrant 4. So I'm just going to go looking in quadrant 4. As a matter of fact, I'm not even going to use this much of the picture. I'm simply just going to use quadrant 4 on my unit circle. And I want y to be -1/2. So I want the angle that hits right there on the circle. This angle right here, where the y coordinate is -1/2. Well, I know exactly which angle that is. That's where this is 30 degrees. So this is -π/6. Right, we've been doing these angles for quite a while now. So the angle I would need to draw that's between -π/2 and π/2 that gives me the sine ratio of -1/2 is -π/6. So arc sine of -1/2 is -π/6. Let's try another one. We're going to switch it up and use that other notation. So I've switched it to, and we've got this little -1 notation in the superscript position. That also means inverse sine. So my parent function is inverse sine of x, and I'm now evaluating it at √3/2. So again, just like up here, I'm being asked to find an angle between -π/2 and π/2 whose sine ratio is √3/2. Well, sine is positive in quadrant 1, and quadrant 1 is one of the places I'm allowed to exist for inverse sine. So I'm just going to draw that part of the unit circle. And I want y to be √3/2. So that would be, what's that, about 1.7.85. So it's going to be up here somewhere. And I need the angle that goes there. So I need y to be √3/2. Ooh, but again, I know what that is. The angle across from √3/2 on the unit circle is 60 degrees. So this is π/3 radians. So there we go. I've got it. I've got the angle that gives me that sine ratio. So inverse sine of √3, I'm going to use parentheses just to make this clear, of √3/2 is π/3 radians. Okay, well, next up is I want sine of 2. I want sine of 2. But here's the problem. If I have y equals inverse sine of x as my parent function, remember we defined it earlier. Inverse sine of x has a domain of -1 to 1. Well, I'm being asked to evaluate inverse sine at 2. That's not in the domain. So inverse sine of 2 is undefined, since 2 is not in, oops, said it right, wrote it wrong, not in the domain of y equals inverse sine of x. So there is no angle where sine equals 2. If you don't believe me, try to draw a circle. Go try to do your unit circle, and go try to find an angle where y is equal to 2 when your circle only goes out to 1. So if your circle can only go out to 1 in either direction because the radius is 1, how are you going to get an output? How are you going to get a y coordinate of 2? And remember, even if you allow the radius of your circle to be 2, even if you allow for that, remember how the sine ratio works. It's the y coordinate off the circle divided by the radius. So if you let your radius be 2, then even if you can get a y coordinate of 2, that 2 over 2 still reduces back to 1. So, but I'll leave that as a challenge. See if you can take a circle centered at the origin with a fixed radius and see if you can get a sine ratio of 2. Okay, sketch a graph of inverse sine. Sketch a graph of inverse sine. Okay, I mean, that's not as difficult as it sounds. So here's our parent function. We know its domain. It's -1 to 1. We know its range is negative pi over 2 to pi over 2. And then if we just get a few coordinates, we don't need a ton. We don't need a lot of coordinates, right? If we just get a few coordinates here, let's do that. So for example, for -1, I need an angle where sine is -1, and that angle can only be negative pi over 2 to pi over 2. Well, thankfully, negative pi over 2 fits the bill, right? If you don't believe me, draw it. Draw negative pi over 2 on the circle. You'll get a sine ratio of -1. Let's keep going. Let's say I had -1/2. That'd be negative pi over 6. Let's say I had 0, that'd be 0. If I have a half, that'd be pi over 6. If I do 1, that's pi over 2. I can do as many coordinates as I want. If I need to use a calculator, I can, right? Because we don't know how to evaluate. There's lots of angles for which we don't know the sine ratio precisely. All right, so let's see. X goes -1 to 1. So if this is -1 and this is 1, negative pi over 2 to pi over 2. If we plot these coordinates, -1, negative pi over 2, -1/2, negative pi over 6. So where would that be? That would be, let's see, -1/2, and then about a third. So like right there. Then 0, 0, and then about a half and a third again. Then 1 pi over 2. We saw the shape earlier on GeoGebra, right? It looks like this. Done on a computer, looks much better. Oh. Looks like that. So this is y equals arc sine of x. You can put x in parentheses or not. It's usually not too confusing one way or the other. But notice it has endpoints. Notice it has endpoints. So I've made that clear here. This thing terminates. It doesn't keep going. It does not keep going. Now, why does it have endpoints? Because its domain is -1 to 1. So domain is -1 to 1 because y equals sine of x had a range of negative 1 to 1. All right, so it's why we got endpoints here. All right, so that's the parent function for inverse sine. That's what its graph looks like. That's what its shape is. So you can apply all the transformations to that and get various, adjustments to that graph. Okay, so what about the other two? What about inverse cosine and inverse tangent? All right, so I'm not going to spend as much time going through the restrictions and why we need the restrictions because it's all for the same reasons, but I will hit the highlights. Okay, let's start with the cosine function. So here is cosine. This blue one right here is cosine. Notice it has a relative max at 1, 0, 1, which parent function for cosine has that. But it still looks like sine, right? It's a sinusoidal function because it oscillates back and forth between negative 1 and 1, just like the sine function. So it should be no surprise then that we're going to run into the same issues with cosine when we go to do its inverse. So if I do its inverse, I get this. That's the inverse of cosine. Notice it fails the, let me get rid of cosine here. Cosine's gone. Notice it fails the vertical line test miserably. I can hit that graph over and over and over again with a vertical line. So it's not a function, which we would prefer it to be a function. So we're going to do the same thing with cosine here as we did with sine. We are going to restrict the domain, but I want to keep the range. So I want the range to go from negative 1 to 1. I want to keep that. I want that to stay the same. I want to be able to get it. If original cosine could output anything from negative 1 to 1, then I want to allow inverse to input anything from negative 1 to 1. So we have lots of options here. For example, we could just do, so here's the original. We could just do this part, go from negative pi to 0. So if you look at this piece of cosine, there's regular cosine. I just want that piece. Regular cosine, that piece. Regular cosine, that piece. This piece will pass the vertical line test and pass the horizontal line test. Therefore, it's 1 to 1, and the inverse will be a function. All right, that's fine. That'll work. But notice it only allows for negative inputs, and it allows for 0. So it does allow for 0, but then it doesn't. Essentially, we're excluding any positive input. And as you know, positive numbers tend to be used more than negative numbers. Not that they have to be, but usually if we're modeling something in the real world, we kind of like to have positive numbers. So another option, so here's regular cosine. Another option would be to use this piece, where we just go from 0 to pi. Now it allows for an input of 0, 0, 1, and it allows for positive numbers, but it doesn't allow for negatives. Ugh. Okay, so we're kind of stuck here. Would we rather just not allow negatives, or would we rather not allow positives? So over time, people have decided, you know what, it's better just to not allow negatives. Let's go ahead and do the positive one. So this is the common restriction for regular cosine is 0 to pi, this piece right here. And if we use this piece right here, there's the inverse. So if you take all these coordinates that are on this blue curve and reverse the positions of the numbers, you get this orange curve, which is part of inverse cosine. So there's inverse cosine that's not a function, the black curve. There's the one that is a function, the orange curve. So all that to say, we're going to restrict cosine to be 0 to pi. So regular cosine is going to get restricted so that its domain is 0 to pi. All right, so here we go. Let's write that down formally. So let's say x equals cosine of y, that's the inverse, is equivalent to y equals arc cosine of x. You can use parentheses around the argument if you want, if you feel like that makes it a little bit more clear that that's the input. So we're going to restrict the domain of regular cosine to be 0 to pi, which means that now becomes the range of inverse cosine. And then the range of regular cosine becomes the domain for inverse cosine. So it's very similar to inverse sine, where the domain's -1 to 1, because that was the range of the original trig function. We restricted the domain of the original to get this range right here of 0 to pi for inverse cosine. Well, that leaves us tangent. So the inverse of tangent is going to be x equals tangent of y. We just changed the places for x and y, but we don't like that version of it. We like y to be by itself. So then we get arctan. Now remember, tangent actually had a range of all real numbers, so its domain's going to be all real numbers. So inverse tangent is nice. It allows you to plug in anything you want. So x can be any real number. However, its range cannot. We're going to have to restrict tangent just like we did sine and cosine. Okay, so let's go see why. Okay, so let's focus on the tangent function and what we need to do to its inverse. So here's the tangent function in all its glory, right? It's got all these branches. We've got all these vertical asymptotes. Here's 2 of them. There's 2 of the vertical asymptotes at pi over 2 and negative pi over 2. So if you're at the top of the unit circle and bottom of the unit circle, the tangent ratio is undefined because you're dividing by 0 when you do your coordinate off the circle. So if you just simply reverse all these coordinates and get the inverse, you get this crazy thing. It looks like it terminates, but it doesn't. It's just software struggles to graph all the coordinates close enough to the asymptotes. It's just kind of a struggle for it. But so you got to. This actually does keep going. This one keeps going. This one keeps going. We get this crazy thing. That's clearly not a function, right? It would fail the vertical line test. So we don't want that. We don't want that. So here is regular tangent. So once again, we want to keep the range. So I want all real numbers possible when I do my restriction. I want all real numbers possible when I do my restriction. And I want to make sure it passes the horizontal line test. So for this one, it's a little bit more clear. If I just keep one of these branches, I'll get the job done. So for example, if I keep this branch right here, that branch goes forever in the positive y direction and forever in the negative y direction. So it'll keep the range. And if I keep just this branch, it'll pass the horizontal line test and the inverse will be a function. The downside is it only allows inputs that are negative. Whereas if I come over here and grab this branch, it allows inputs that are only positive. Okay, well, it'd be nice if we could do both. And sure enough, this branch right here near the origin, it allows for negative inputs, positive inputs, and 0. So this branch right here through the origin is just the natural, just kind of makes sense to use that as my restricted domain. So we're going to restrict the domain to be negative pi over 2 to pi over 2. We're just simply going to use that middle branch. So here's the whole one. There's the one we're going to use. There's the whole one. We're going to use this one because it passes the horizontal line test. It passes the vertical line test. So it's 1 to 1. So the inverse will be a function. And sure enough, there's the inverse. So here's my orange one. That's the inverse. And that is going to be a function of x. Now notice, though, the original is contained between 2 vertical asymptotes. So the inverse is going to be contained between 2 horizontal asymptotes. So inverse tangent is sandwiched between 2 horizontal asymptotes. All right, let's go back. So we've just seen that inverse tangent can only output negative pi over 2 up to pi over 2. However, those are the locations of asymptotes, so you can't equal those, which should make sense because you weren't allowed to plug in negative pi over 2 or pi over 2 to the regular tangent function. It was undefined, so they can't be outputs of inverse tangent. All right, so let's sketch a quick graph for each of those just so we know what the parent function's graph looks like. So we'll sketch cosine and arctangent. Remember, this one has a domain of -1 to 1 and a range of 0 to pi. Right, so pi is a little bit bigger than 3. So if we do that, pi, that'd be pi over 2. If that's 3, then okay, so that scale should fit everything. So when x is -1, you'd have pi, because pi -1 is a, oops, let's move this to the other side. So -1 pi, and then when x is 1, then cosine of 0 is 1. So we'd have 0. So since cosine of 0 is 1, then 1, 0 is a, go back to blue here. Then we'd have 1, 0. And then when you're at the top of the circle for cosine, you have, so pi over 2, cosine of 0, so 0 pi over 2. So we're going to get our little shape there. It's a little more squeezed than I guess it needed to be, but that's okay. All our coordinates are there. Oops. So we got this and this. All right, so that's y equals inverse cosine. Let's see, for tangent, you're allowed to plug in any x you want. But the outputs will always be bound between -pi over 2 and pi over 2. This one's a little bit easier to graph. So if this is pi over 2 and this is -pi over 2, those are your asymptotes. And then tangent goes through, the original tangent goes through 0, 0. So inverse will go through 0, 0. And then you know that tangent of pi over 4 is equal to 1. So then 1 pi over 4. So if that's 1 and that's -1, then you know 1 pi over 4, -1, -pi over 4. And then we know what the shape of one branch of tangent looks like. So there's y equals inverse tangent. And it does go on forever because its domain is all real numbers. But it is sandwiched between those two horizontal asymptotes. All right, so let's practice finding values off of those functions. So let's start with inverse cosine. So let's say I've got my function inverse cosine of x, and I want to evaluate it at root 2 over 2. So I'm looking for an angle where cosine's ratio is root 2 over 2. So this is a ratio from our circle. Okay, so inverse cosine, right? Remember, inverse cosine is between 0 and pi. Well, cosine is positive in quadrant 1. So I know I'm in quadrant 1. I'm in quadrant 1, and I want root 2 over 2. Well, root 2 over 2 is right here. That's where x is root 2 over 2, and I know exactly what angle does that. Thanks to geometry, that is 45 degrees, or pi over 4. So inverse cosine of root 2 over 2 is pi over 4. Well, what if we did tangent? All right, well, let's do tangent. So what if I had inverse tangent of x and I wanted to plug in 0? I want to plug in 0. So again, this number 0 is the ratio from our circle. And remember, inverse tangent is sandwiched between negative pi over 2 and positive pi over 2. So if I'm at 0, remember, tangent's ratio is the y-coordinate from the circle divided by the x-coordinate off the circle. So if this is my circle, the only way that I'm going to get a ratio of 0 for tangent is if I'm over here at the far right. Because then my y-coordinate is 0, and 0 divided by 1 is 0. So I would be at this angle right here, and that angle, as we know, is 0 radians. So inverse tangent of 0 is 0. Right? The graph of inverse tangent went through the origin, so now we see why, because that's the angle you'd have to draw to get a tangent ratio of 0. Let's do another tangent one. So what if I had inverse tangent of x, and I wanted to evaluate that at -1. So again, this is the ratio, and I've got to be between negative pi over 2, so I can come down here to get an answer, or I could come up here and get an answer. But I want -1, so I can't do that in quadrant 1. Those are all positive numbers, so I got to be down here. So it's going to be in quadrant 4. And I want y divided by x to be -1. Well, I know exactly where that happens. It happens where x and y are the same thing. So if I go right √2/2 and down √2/2, so it'd be this angle right here, which is -pi/4. So inverse tangent of -1 would be -pi/4. Okay, next up. Remember, to define inverse, when we defined what inverse functions were, we said that the definition was if you plug the inverse into the original and it returns back to you the original input, you were on your way to being inverses of each other. But the reverse should be true. You should be able to plug the original into the inverse and be returned back to the original input x. Both had to be true. And then, if that's the case, those are truly inverses of each other. However, since we placed all these restrictions on the regular inverse trig functions, we got to be careful when we go to use this definition to help us out. So let's revisit that definition and see when we actually can use it because of all these restrictions we placed on it and when we can't. Okay, so for example, let's say I take the sine function and I input inverse sine. Well, normally, inverse sine and sine would negate each other and you would just get x. I mean, that's how inverses are supposed to work. That is true. That is true. However, we have to be careful. That's only true because remember, the domain of inverse sine is -1 to 1. So that's only true if x is between -1 to 1. If I reverse it, and let's say I input sine of x to its inverse, they should negate each other and give me back x. But we got to be careful. That's only going to be true if x is between -pi/2 and pi/2, because we restricted regular sine so that its inverse only output -pi/2 to pi/2. So we got to remember all those restrictions we placed before you just go applying the definition of inverse functions willy-nilly to the trig functions. So then, all right, next up would be what if we had cosine? Don't know why I used brackets. I guess there's no real need for those brackets. So what if I did cosine and then I input inverse cosine? Well, it should equal x. I mean, that's how inverses work. But we got to be careful. That's only if x is between -1 and 1, because that's the domain of inverse cosine. If I reverse it, it will output x as it should, but only if x is between 0 and pi, because we restricted everything so that inverse cosine only ever gave me back an angle between 0 and pi. And then tangent, all right, so tangent, so if I'm plugging inverse tangent into tangent, well, remember, inverse tangent allows for a domain of all real numbers, so x can be any real number. But if I reverse it, then x has to be between -pi/2 and pi/2, because the outer function's inverse tangent. Inverse tangent's only allowed to output numbers between -pi/2 and pi/2. Okay, so let's put those to some use. So I've got regular tangent here, and inverse tangent is being plugged into it. So inverse tangent being plugged into tangent, x can be any real number. X can be any real number. Well, -5 is a real number, so that works. That's in the domain. So this output will be -5, since x equals -5 is in the domain of arctan of x, and the range of the tangent function. So we're good. That tangent and that inverse tangent, they just negate each other. They're inverses, so you'll just get -5. All right, well, arc sine and sine, they should negate each other, right? We're hoping this just equals 5 pi over 3. That's the idea. Well, let's see if they will. So 5 pi over 3, that needs to be a possible output for inverse sine. Well, 5 pi over 3, if you think about where 5 pi over 3 is at, let me draw a slightly bigger picture here. So if you draw 5 pi over 3, that's 300 degrees. So that's down here. But that's not one of the angles that inverse sine's allowed to be. Remember, inverse sine's only allowed to be a negative angle down to here or a positive angle up to here. So those are not equal. So inverse sine of 5 pi over 3, well, instead of being, so we know that 5 pi over 3 hits the circle right here at this coordinate. That's 60. So this is at 1/2, so my picture's not very good. -√3 over 2. My scale's not great there, sorry. But that angle is not allowed. It's not a possible output for inverse sine. But we can come up with one that is. So instead, why don't we do, here, let me see if I can grab another color that's easier to see. So why don't we do instead this negative angle? Why don't we just do -pi over 3, which would get me to the same coordinate. And -pi over 3, it'll get me the same coordinate that 5 pi over 3 does, and it's an angle that's actually allowed to be output by inverse sine. So this is actually equal to -pi over 3. So this is what we mean by you got to be careful. Normally, functions and their inverses just kind of undo each other, and you just get back x. But since we placed all these restrictions on some things, you got to be careful. And if it's not within the restrictions, you got to go find something that is. Let's try this other one here. We're going to do inverse cosine and plug it into cosine. And pi is our input for inverse cosine. But pi is not, so this does not equal pi because pi is not in the domain of the inverse cosine function. Inverse cosine of pi is undefined. So the very first thing you try to do, inverse cosine of pi, I mean, that's not even a possibility. That's not a value. That's not even a number. So therefore, cosine of inverse cosine of pi is undefined. Again, this is just trying to show us that you've got to be careful. You can't just see, oh, look, inverse, these two things are inverses, so they're going to undo each other, so the answer is pi. You can't just say that. You got to think about what the numbers are and the restrictions placed upon the domains and ranges of these functions. Otherwise, you're going to find yourself in a sticky wicket.